So, B part 6, exterior algebra. Lecture 10, example of Gauss's or divergence theorem in R3. Problem statement. Let a vector field be f, a function of x, y, and z, is x2, y2, and z2. Let the region V be the unit cube in R3. You see, that is, the volume V, x, y, and z belongs to R3. X, y, and z stays between 1 and 0. That's a unit cube. So, task. Use the exterior algebra to compute the flux of F across the boundary. See, partial of V is the boundary of V. Using, in this case, you see the Gauss's theorem. Look, I would like to emphasize that this Gauss's theorem is given by advanced calculus. Okay? But I want to use the Gauss theorem in the exterior derivative. You see, exterior algebra, okay? It will be the exterior derivative over here. So we will compute both sides of 1 of this here using exterior algebra, you see? Now, let's move to step 1. Express the flux form. Recall that the flux form omega belongs to the two-form space, you see, embedded in R3. This flux is associated to the field F, F1, F2, F3, exactly as we did in the previous lecture 9. So then this omega is F1 dy dz, wedge dz, F2 dz wedge dx, F3 dx wedge dy. Now remember, you see, dy, you permute. See, dy, this case, in dz, the next of dy is dz, next of dz is dx. Now you look at here and move dz, dx, dx, dy. Remember, dx, dy, where dx is analogous to the vector, unit vector k. You see? Likewise, dy wedge dz is unit vector I in the advanced calculus. And dz wedge dx is analogous to the unit vector j in advanced calculus. You see? That's what we did before. Now, for f, x2, y2, and z2, we get omega, we associate, you see, the omega here, the f is x2 dy dz, y2 dz dx, and z2 dx dy. Step 2, let's compute dy. You see, d omega. Omega is a form, the scale form 2. D omega belongs to the form 3. You see this 3 over here. See? Both are embedded in the R3. Both are the omega 2 and omega 3. They are embedded in R3. Now let's use the exterior derivative. You see, d omega, you see, is d. I just copy, okay, this omega over here, this omega over here. You see, I'll set here just for be clear. This is a blue one here. You see, there's a blue one. I repeat over here. Now, according to lecture 9, the previous lecture, you see, partial derivative of 1 respect to x, partial f2 respect to y is 2y, partial f3 respect to z is 2z. I just substitute, you see, d omega 2x plus dy plus 2z. This is the volume, dx, dy, and dz. Now, phase 1, you see this figure here, okay, will clarify for you. That's a unit cube. You see, this is x-axis. You see, the green one is x is equal 1. The blue one is x is equal 0. Just to you follow here, you see, so the phase 1, you see x is equal 0. That's a blue one over there. So n is equal minus 1. N, by definition, okay, points only out of the surface, okay? That's n is equal minus 1 at x is equal 0. So this f is 0, 0, 0 because in this case x is equal 0 and y is equal 0 and z is equal 0. So f dot n is 0. Now, likewise, the phase 2, you see the green one, the phase 2, in which x is equal 1. So n is plus 1 here, 0, 0. And f is x squared, which now is 1, y squared and z squared. So, analogous to this figure here, phase 3 and 5, f dot n is equal 0. And phase 4 and 6, f dot n is equal 1. You just substitute here, you get 1 plus 1 plus 1, which leads to 3, okay? I call this relation 2. Now let's move to the right-hand side. You see, let's move here to the right-hand side, okay? And the volume integral. Now, the volume integral of the omega, you see, I just substitute here. This is equal to 2x plus 2y plus 2z. This is a volume element, okay? dx, dy, and dz, you see? Now, you see, I expand, okay? I expand these three terms over here, this term, and this term. You see, dv is a blue one, okay? Is a volume element. Now, it's clear that the integral, I'll show here the three terms. This one is this one. You see, let's go to this first one. You see, I have 2 integral x dv. Now, this is, this case, you just expand this, you see. Now, this is x, you see, x dx. Now, I repeat, x dx, integral from 0 to 1 to dy, integral from 0 to 1 to dz. Okay, and this over here will be 2 times. This is 1/2. Why? Because integral x dx is x2 divided by 2. Between 0 and 1, this leads to 1/2. So I have 2 times 1/2 times 1, which is 1. Likewise, the same. You see, this is integral, the second one over here, is 2 times the integral of y dx dy dz. You see, this is 2, 0 to 1 to dx, 0 to 1 to y dy. Attention now. You see, and this is 0 to 1 to dz. So it's 2 times 1 times 1/2 times 1. This is equal also to 1. Now the third one, 2 integral of z, this volume over here. This is from 0 to 1 dx, 0 to 1 to dy, 0 to 1 to z dx. You see? Because you see z over here. So this again, 2 times 1 times 1 times 1/2, which is 1. Now we can add. You see? If you add this, you have 3 over here. And then you compare. You see? The relation 2 and relation 3. Relation 2 and relation 3. This is the application, okay, of the divergence theorem or Gauss's theorem, okay, using the exterior algebra. That's it.